Now let's look at this question. Now this is a question that comes from the 2024 exam, the May-June 2024 exam. I'll put it right here, May-June 2024, and this was paper 21. So this is from the May-June exam for AICE chemistry, and we're going to do this question because it actually brings together both mass spectra and IR spectra. So we're going to look at both mass spectroscopy from 18.8 and IR spectrum from 18.7. Now, this question is particularly good because it does both. It brings in an actual picture of an IR spectra. For the mass spectra, we never get to see the spectrum. And this is very typical Cambridge. You don't always get the spectrum, right? You don't always get the full spectrum. Sometimes they'll give you pieces of information and you need to know how to work with the spectrums or with the information given in the spectrums in order to figure out certain things. So let's look at this one, for example. Compound W has a molecular formula C4H10O. So very important here, they give us both compound W, they tell us what it is, as far as its molecular formula. So this is very important information. So something we might want to highlight or underline. And they even tell us it contains only one functional group. So we know that there's not going to be more than one functional group. That might be useful for later information, especially when we get to IR, because remember, IR spectroscopy is all about functional groups. Table 5.1 shows two peaks with the greatest ME, or mass to charge ratio values, in the mass spectrum of W. So here we have the mass spectrum information. Notice how we don't get an actual mass spectra. We don't get what the mass spectrum actually is. We just get information. They tell us we had two peaks, 74 and 75. And they give us the relative abundances, which are 50 and X, right? So X meaning that we're probably going to have to find them. So if we keep reading, because we haven't actually, this is all prior information, the first question says, calculate the relative abundance X, so we need to figure out what X is, of peak at ME75 using the information from table 7.1. So here we need to figure out what the relative abundance of the peak at mass to charge ratio 75 is. Now that's not something that we have talked about or that's something we have studied, but it is something that you should, with a fair amount of critical thinking, be able to figure out. Why? We only know one piece of information from the lecture on 18.8 that relates to the relative abundance of the peaks. And that is an equation. We learned that the number of carbons, N, in a compound is equal to 100 divided by 1.1 times the relative abundance, so we'll call this AB for abundance, of the peak, this is M plus 1, over the relative abundance of the peak, at M plus. So this is the equation that we learned during the lecture. We learned how to relate the relative abundances of the M plus 1 peak and the M plus peak to give us a number of N, or the number of carbons. Now, you might be saying, okay, yeah, that relates to abundance, but we're not being asked to find the number of carbons. But if we remember, we were given the number of carbons. We know the number of carbons is 4. So from that equation we know, or the chemical formula, we know N is equal to 4, and that's going to be equal to 100 over 1.1 times the abundance of the M plus 1 peak. How can we know if this is the M plus 1 peak or not? How can we know if this is the M plus peak or not? Because we have two peaks, but we don't necessarily are told that they are the M plus or the M plus 1 peak. But we can easily figure that out from the chemical formula. We know the molar mass of carbon is 12. We know the molar mass of carbon of hydrogen is 1. And the molar mass of oxygen is 16. Well, in this formula, there are 12 carbons, there are 4 carbons times 12 plus 1 or 10 hydrogens times 1 plus 1 oxygen, which is 16, gives us a total molar mass for this compound of 74 grams per mole. Because the molar mass of this compound is 74, we know that this 74 peak has to be the M plus peak. And therefore, if the molar mass of the compound is 74, and that's the M plus peak, then the peak at 75 has to be the M plus 1 peak, because it's 1 more than the molar mass. So that actually means that 50 is the abundance of the M plus peak. So this is only 50. And then the X is going to be the abundance of the M plus 1 peak. So what does that leave us? That leaves us with an equation that we can easily solve if we have some algebra skills. 4 is equal to 100x, because we multiply the top, over 5 times 50 times 1.1. We just here, all we need to do is solve for x. So we have x is going to, I'm going to go up a little here. X is going to be equal to 4 times 50 times 1.1 over 100. And that's going to give me x. 4 times 50 times 1.1 divided by 100 gives me 2.2. So what is, oops, let me make that a little better. So it gives me 2.2, which is x, or the abundance for the M plus 1 peak, the 75 peak. So we're using the equation that we learned for mass spectra. We're using the mass to charge ratios and the fact that they're equal to the molar masses. We're using our knowledge of relative abundance. We're just not actually looking at a mass spectra. But all of this information comes from that lecture. And that's something that's very important to realize. The questions will not necessarily just give you a spectra and ask you what is it or to use it. Sometimes you'll have to get creative with how the spectra are used. Now let's look at this next question here. I'm going to change the color. The mass spectrum of W, so we're still talking about W, same compound, shows a peak at 29 and at 59. Suggest molecular formula of these fragments. So here we know that we have a 4-carbon compound. So 1, 2, 3, 4, with an oxygen. So it could be a carbonyl, it could be an alcohol. We don't know what that is yet. So we just know we have a 4-carbon chain with something attached to it. We'll just put a question mark. Or it could be an OH, it could be a carbon double bond oxygen. But we don't really need to know what the compound is, because what we know is that we have a 59 peak and a 29 peak. What we have to figure out is what combination of carbon, hydrogen, and oxygen, because that's the 3 elements we have here, could give us those numbers. We know carbon has a molar mass of 12, hydrogen has a molar mass of 1, and oxygen has a molar mass of 16. So we'll start there. This is where we should always start our musings in, is what combination of these compounds could give us these particular peaks. Now, we actually saw some common peaks in the lecture. And we know that peak 29, the ME or MZ, depending on which mass spectra you're looking at, 29 has a very common source, and that is a CH2CH3 peak. Carbon has a mass of 12 times 2 carbons plus 5 hydrogens in total. That's 24 plus 5 is 29. This is where knowing these common peaks is going to be useful, because instead of having to then put together, okay, 2 carbons and then how many hydrogens, instead of having to put all that together, we could easily remember these. Now, if we don't remember that 29 is a common peak and it's caused by a CH2, CH3, we could just start adding up. So if we have a carbon, we're always going to have carbons, right? So if we have a carbon and an oxygen, for example, C and an O, that's 16 plus 2 is 28. So then that would mean that we would only add one hydrogen. And that doesn't make sense, right? CHO is not something that we find very commonly other than in aldehydes. So even though that could be an option, and you could put it, it's more than likely going to be the CH2, CH3 peak. And let's always remember, because we are working with mass spectra, that we're asked for the formula, we need to put the plus charge on it. If you answer these questions and you don't put the plus on your answer, you're not going to get the right answer. You're not going to get it counters right because these are fragments, meaning they want to see the +1 charge. Now, for that takes care of the 29. The 59, it's a little more intense. Now, one of the things you can do here is use your prior knowledge, right? So you know CH2, CH3 peak is going to be 29. So this minus 29 gives us 30. So we could have a CH3, CH2, and then something else on it. And that's when you can start getting creative and adding things to your formula. So if we add another carbon, for example, that would be another 12. And so we have 18 left. Well, if we have 18 left, we could add another oxygen, and that's minus 1 is 2 left. So what can we add that has 2? Well, 2 hydrogens. So we could add another CH2, which will make sense as far as a chain is, and then oxygen, which could be a carbonyl, a carbon double oxygen, or it could be a CHOH. It could be an alcohol as well. So another fragment could be a C3H7O+. Now, don't get stuck on, is it a carbonyl or is it an alcohol? Doesn't matter. If you read the question, they don't ask us for what functional group is creating that fragment. It's just, what is the fragment? How many carbons, how many hydrogens, how many oxygens? They don't give us enough information here to make an educated guess yet about what the compound is. So when they're asking about the fragments, what they want to see is fragments that make sense as far as the molar masses. So there being 3 carbons, carbon having a molar mass of 12, there being 7 hydrogens with a molar mass of 1, plus a 1 oxygen with 16, they want to make sure that this adds up to the 59 for the fragment. 3 times 12 is 36, plus 7 is going to be, and I can do basic math, 43, plus 16 is going to be 59. So this does check off on that necessity. Are there other answers that could be valid? Yes, assuming that you are thinking about, how many bonds a carbon can make. So something like, for example, let's say for the 29 here, if you put something like CH, I don't know, 29 minus 12 is 17. CH17, that obviously is not going to fly. Yes, this adds up to 29, but carbon cannot have 17 bonds on it, right? So just make sure that you have a good idea of what adds up and what is realistic. This could also, by the way, have been written as C2H5+, and that would also be a perfectly fine answer. So, now let's keep going with these. There's a follow-up to the question. So this question now goes from a mass spectra part of the question, with that equation that we talked about for number of carbons, the peaks, and the fact that they add up to molar masses, to then transitioning to an IR, an infrared spectroscopy question, using the exact same compounds. Now, if we look here, and let's change colors again. A sample of W, so we're still talking about the same W, right? C4H10O, is heated under reflux with an excess of acidified potassium dichromate until there is no further reaction. Only one organic product X is present in the mixture at the end of the reaction. So now we are bringing in chemical organic reactions into this question. It's not just about the spectra anymore. We do have information. We do want to write it down. I would highly suggest that here on the side of the test, you do write things like, for example, W, when it reacts with K2Cr2O7, potassium dichromate, and heat or reflux, is going to give us X, right? Because this is going to help you. If you remember that this is an oxidizing agent, you would know that this is an oxidation reaction. So we're looking for a W, a compound that can be oxidized. So what's that going to rule out automatically? It's going to rule out things like alkanes, for example. Although we do have an oxygen, but alkanes can be oxidized by dichromate. That's not a reaction that we learned. So we can start narrowing things down using the reactions that we learned. So figure 5.1 shows the infrared spectrum of W. So here we have W, and then figure 5.2 shows the infrared spectrum of X. So we are given the infrared spectra of both X and W. And you see I can now go farther down and look at these because I already wrote this here, so I don't need that information anymore. So we have here the spectrum of the IR for W and the IR for X. Now remember what we talked about. When we are looking at these, we're looking for very specific things. We're looking for example, this right here, this very wide peak in the 3000s, that tells us that that compound, W, has an OH in it, meaning it's a carboxylic acid, an alcohol, and that's about it. The very deep 1700 peak, that's very narrow here in X, tells us that there's a carbonyl, C double bond O, on it. Meaning that this is either a carboxylic acid or an ester or an aldehyde or a ketone. But because there is no large peak here, we know there is no OH in X. Meaning there's a carbonyl but no OH, meaning X is not a carboxylic acid. So just from looking at these, I haven't even read the question. I can tell that just by identifying those big things. And also because this is A, this is B, they're probably going to ask us about it, right? Because like I said, even though technically in the curriculum, you have all of these other peaks, like the amide peaks and everything in IR spectra, a lot of the questions in my experience are just going to revolve around OHs and C double bond O. That's why IR spectrum is in chapter 18. Chapter 18 is the carbonyl chapter, meaning aldehydes, ketones, esters, and carboxylic acids. So we're going to focus a lot on these two peaks right here. Most of your IR questions will be about whether these two peaks are there or not. So let's look at the actual question, right? Because we haven't read the question. So they give us the chart for, right, our IR spectrum. And then it says, in question I, absorption A is shown in figure 5.1, absorption B is shown in figure 5.2. So we're looking at these and we're looking specifically at A, so the peak that we highlighted before as being an OH peak, and B, the peak we highlight as being the carboxylic acid or the carbonyl peak. Now we can double check that, right? If we go down here, we can see that the carbonyl peak is supposed to be around 1710 to 1750 for an ester, 1670 to 1740 for a carbonyl carboxylic acid or a carboxyl carbonyl. Notice, are we going to look at 1640 to 1690? No, we don't care about this. Why? This is for an amide. Amides have nitrogen, and if we go up, remember, we're still talking about our original W here. W did not have nitrogen in it, C4H10O. So we can use that information to say, okay, we can ignore that amide because it's not going to be an amide because there is no nitrogen. We then can also look for this 1700, for the big wide 3000 peak, around 3300, and we can see that around 3300 we have that hydroxyl OH peak. Now, is it definitely not going to be a carboxylic because it's 2500 to 3000? Not necessarily, because remember, these are going to be a bit of a suggestion. They could be higher than that or lower than that. But what does tell us that this is not a carboxylic acid is that there's no 1700 peak. So because there's no deep narrow peak here, 1700 in this one, we know this has to be not a carbonyl. It doesn't have to have a carbonyl. So more than likely, and this is not set in stone, but as you come up with ideas, write them down, more than likely this is going to be an alcohol, and this, which has the carbonyl peak, but not our Y peak, is either going to be a ketone or an ester. Or, actually, an aldehyde. Now, we can actually eliminate one of these if we think about it really hard. And this is where knowing a lot of different parts of chemistry come into play when it comes to organic chemistry questions. We can eliminate one of these. Why? If we read the question again, a sample of WC4H10O is heated under reflux with an excess of acidified dichromate until there is no further reaction. So it's oxidized, because remember, K2Cr2O7 is an oxidizing agent, or an oxidation agent. This is an oxidation agent, meaning it's oxidized until it cannot be oxidized no more. That means we can actually get rid of aldehydes. Why? Aldehydes can be further oxidized. Remember, primary alcohols can be oxidized into aldehydes, which can be further oxidized into carboxylic acids. Because aldehydes can be further oxidized, this W cannot be, cannot be an aldehyde, because there's no further reaction. Meaning that this has gone all the way through and therefore could not be an aldehyde. Also, because of that, and because we know this is not a carboxylic acid, this alcohol can't be primary. So we're finding out a lot of information just from putting all these pieces together. It is a very high, difficult, critical thinking question where you need to remember a lot of different parts of what you learn about organic chemistry. But let's read the actual question, right? Because I'm going around trying to figure out what these are, but I haven't read the question. Complete table 5.3 using the information given in figure 5.1, figure 5.2, and table 5.2. So here they want to know for absorptions A and B. A and B. What are the bonds? And what is the functional group containing that bond? So what we know now is that we know A, because of that white peak, we know it's an alcohol. We know it cannot be a carboxylic acid because there is no peak at 1700. So we know it's an alcohol, meaning we can actually answer this question right here. So let me change my color. So what is the bond? Well, we know the functional group is an alcohol or hydroxyl, whatever you want to call it. And what bond is in the alcohol? What is the bond responsible? Here's where you got to be careful. Don't just put anything here, because alcohols do have technically two bonds. In an alcohol, there's going to be the bond between the carbon and the oxygen. So that's bond number 1. And then there's going to be the bond between the oxygen and the hydrogen. That's bond number 2. So there are two bonds to choose from here. How do we choose? if we go up to our chart, this peak, the A, which we're talking about, is around 3,300. The 3,300 peak for hydroxy or alcohol is the OH. There is this CO bond for hydroxy, which again is alcohol hydroxy, but that's at 1040 to 1300. This 1040 to 1300 is roughly around here. This one right here. This peak right here is our CO peak. But that's not the one we're talking about. Actually, oops, I went to the wrong mass spectra. That's not the one we're talking about. So here it is. So this peak right here, let me change my color. That color is not great. This peak right here is our CO peak. The peak right here is the OH peak because it's at 3,300. So be very careful when you answer these questions that you're looking at your chart and putting what the chart says under bond. Also, if you're confused as to what bond means, look at your chart. The title of this column is bond, so that's what we put here. Now, we could put hydroxy here and you will still get the right answer. You will get the right answer if you put alcohol as well, however. So this bond right here is the the OH bond. And then for B, on the other spectra, if we go up, this deep, narrow peak right here, strong narrow peak, we said is our C double bond O. Now we are between a ketone and an ester. So what do we put for functional group? How do we figure out which one it is? Here's the good part. We don't need to. Why? Both esters and ketones are part of a bigger family called the carbonyls. The whole thing with chapter 18 was the carbonyl groups. So when we look at our chart again, and always rely on your chart, that deep peak is going to be carboxyl, which we know is not it because there is no OH peak. It could be an ester, or more wildly could be a carbonyl. If you're ever in doubt, look at the specific location. Esters are 1710 to 1750. If this is halfway between 1500 and 2000, this right here is 1750. So this is probably around 1740, around there, 1720. So it's probably going to be on the lower end here. The other thing is that in order to make an ester, there's only one reaction we learned about that makes an ester, and that's the reaction between carboxylic acid and an alcohol. We never learned of an oxidation reaction that can make an ester. So even though we are between ketones and esters, we can actually very safely cancel out esters as a choice because this is an oxidation reaction. And as an oxidation reaction, because we have an oxidizing agent, esters cannot be made. We do not know any oxidation reactions that create esters. So ketones are really the only chance. Now, do you see ketone on here? No, because ketones are going to fall with aldehydes under the carbonyl umbrella. Oops, that is very bad. Under the carbonyl umbrella. So we're not going to put a ketone. We're not going to put an aldehyde. What we're going to put in our answer is what it says on here, which is carbonyl. So what is the functional group? It's a carbonyl functional group. What is the bond? It is the C double bond O bond in that carbonyl. So now we can actually come together and put all of this information that we learned together, because the next question here, the last question we're going to do, there is more to this question 5, but it has nothing to do with mass spectra or IR. The last part of this question says, use the information in A and BI to draw the structure of X in the box in 5.3. So we have W, C4H10O, creating an acidified or reacting with acidified potassium dichromate to create X. So let's put all the information together. What do we know? We know we have, actually, let's go back down. We know we have 4 carbons. So we know that the structures are going to be 1, 2, 3, 4, or 1, 2, 3, 4. That's really the only 2 chain isomers that we can create with 4 carbons. We also know that it's going to be an alcohol that is not primary. Remember, we know this because it's an alcohol because of that OH with no carbonyl. We know it's primary because it has no further reaction. Primary alcohols will be oxidized into a carboxylic acid, and we know this is not a carboxylic acid. We know it's a ketone. Meaning that not only do we know it's not a primary alcohol, we know pretty surely that this is a secondary alcohol. Meaning we are either going to get this right here with an OH on the second carbon, and that could be here, or we're going to get this with an OH in our central carbon. So these are our 2 choices right now. How do we narrow it down? How do we make it, how do we choose one? Actually, wait. So these are our 2 choices. Actually, I should make this a little more clear. These are our 2 choices for W. So how do I narrow it down? How do I figure out which one of these is going to give me X? Again, the answer lies in the reaction. The reaction says that we undergo a reaction with dichromate, which is an oxidation reaction, and there's no further reaction. If we look at these 2 alcohols, one of them is actually, and that's my fault for mislabeling it, is not secondary. Remember, secondary alcohols like this one can oxidize. This is not a secondary alcohol. This is a tertiary alcohol because that carbon that the OH is bonded to has 3 other carbons attached to it. This tertiary alcohol cannot oxidize. That is one of the things that we learn in chapter 17. So this alcohol can oxidize, meaning this is not our W, because W has to be able to oxidize in this reaction. Meaning W is this right here. So this is W. But we're not done, because now we just figure out what W is. We need to figure out what X is. We know X is a carbonyl. We also know that a secondary alcohol can be oxidized into a ketone, which, according to our IR spectra, this could very well be. We have the carbon double bond oxygen, no broad peak on the left side, so this is has to be a carbonyl. It's a ketone more than likely, or it could be an aldehyde. But again, aldehydes can be oxidized into carboxylic acids, so it's not an aldehyde. So this has to be a ketone. So what does this secondary alcohol get oxidized into? This secondary alcohol gets oxidized into the ketone that has the exact same structure, but instead of an OH has an O double bond. So this is what X is. And it fits all our data. It fits everything that we were told about W and X. This is made from this. This is an alcohol, which the IR for W fits. This is a ketone, which the IR for X fits. It has 4 carbons, 1 oxygen, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. The original W has 1, 2, 3, 4 carbons, C4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, H10. and 1 oxygen, which fits our W chemical formula. And finally, if we scroll up a little, it fits our fragments. And don't forget about this because these are useful. We have a CH2, CH3 somewhere on W and a 3-carbon chain with an oxygen. If we scroll down and we look at our oxygen here, I'm going to switch over colors. We have, let me do this one. So we have here a CH2, CH3 fragment that we saw in the mass spectra. And then we have a let me do a different color here. We have a 1, 2, 3 carbon fragment with an oxygen, and I believe it was 7 hydrogens. 1, 2, 3, 4, 5, 6, 7 hydrogens. So it fits the fragments as well. So it fits all our data. This is how we know that we're completely right. Both what we figure out what W was and what X is fits the data we were given. So it's just an example of a paper 2 question that uses both IR and mass spectra to kind of solve a puzzle. And that's what analytical chemistry is. It's a puzzle that we're solving based on the information given by these tools like IR spectroscopy and mass spectra. But you can see it takes a lot of thinking. It takes me a while to explain. I mean, this video is roughly 30 minutes long because I'm explaining every thought process. But eventually, if you get good enough and if you remember enough organic chemistry, you'll be able to do this by yourselves just in your heads without having to write too many things down. I mean, I did write, like I said, a lot of things down, but I'm annotating absolutely everything on the problem. You shouldn't have to do that. So my suggestion is just practice. Go back to different exams, find questions like this, and they're very obvious because they'll have the mass spectra or the MEs or the charts like this, and just practice. Practice the critical thinking because that's the important part here. All right? All right, that is it for this practice problem. I'll see you all in the next video.